Welcome back to Quantum Computation Simplified Part 2. So in this video we will be seeing the minimum essential mathematics which are required for us to do some bit of programming. And all the mathematics what you see in a textbook or a video they're all required, but just for the beginning you don't have to get confused. So I'll try to bring out the minimum essential things here. We'll touch upon vectors, complex numbers, simple matrix operations, then a tensor, product, inner product, unitary matrix, and some more matrix operations, and finally sum modulo 2. So sum modulo 2 will just finish it off here itself. So it's nothing but adding two numbers, divide by 2, and whatever the remainder, that is the answer for sum modulo 2. So here we have been given 0 bit and 1 bit. So 0 plus 0 is 0, we know, and 0 plus 1 is 1, remainder is 1. Only here is slightly different. 1 plus 1 is 2, so remainder is 0. And the people who are familiar with classical gates, they know that this is nothing but XOR or XOR operation. Vectors. So what are vectors? Vectors are, just it's a form of expressing certain things. So they are used to represent quantities that have both magnitude and direction. For example, velocity. So suppose I ask you what velocity you are in, so you have to tell me I'm going at 55 miles per hour in this direction. Otherwise, if I want to catch you, I cannot do it by just knowing the magnitude. So like that, many physical parameters, they're all represented in vectors which need both magnitude and direction. And these vectors can be added, subtracted, and scaled for forming a vector space. So this is a bit confusing thing. For the time being, we'll leave it. What we get from here is vectors can be added. Suppose you have v and w, two vectors. The sum of the vectors is given by like this. So how to do that operation? Possibly I request you to go through the linear algebra book, like how do I do it. It's again simple calculations, and you can scale it like this. So w, and it will become twice the magnitude, and then if you add it, the result will be a longer vector, right? And the dot product of two vectors will be using it. So that is given by an equation like this, wherein you multiply the magnitude. So magnitude is nothing but the distance or the length of this vector. So a length into b length into cos theta. So theta is nothing but the angle between the two vectors. Got it? Very simple. So for some more manipulations, you can go through the linear algebra book. I have given you a reference video, very nice video. And one more quiz for you. What happens if theta is 90 degree? Maybe we will see it again later. And complex numbers. So complex numbers, again, it's a way of expressing certain numbers. So the special thing about this, it has got a real part and an imaginary part. So an example is given here, a plus ib, where a is the real part, b is the imaginary part, and it has got a funny notation I. So where I is defined as I square equal to minus 1, or I equal to square root of minus 1. So this is useful in some of the particularly in electrical engineering. It has got a lot of applications, and every complex number will have its own complex conjugate. So what is conjugate? So wherein you negate the imaginary part of it. So 2 plus i's conjugate is 2 minus I. Interestingly, when you multiply a complex number along with its conjugate, the resultant will be a real number. So in this case, you can see 2 plus I into 2 minus I is 2 square minus I square. So 4 minus I square is plus 1, you get 5. Another expression, it's called Euler's formula, where it relates the exponent form to the sinusoidal function. So e power I pi is given by cos pi into I sin pi. So let's look at how do you represent a complex number. So in order to represent, you need a complex plane wherein this is real axis and this is imaginary axis. So a complex number is represented in this plane. And what is A? A is what is projected here, and this is A, this distance. Similarly, this distance is B. And complex conjugate, you just negate the imaginary piece, so you get the complex conjugate. Interesting. And this is like a Cartesian form, and you also have a polar form, so wherein you can represent a vector, a complex number here, and then pi is the angle it makes with respect to real axis. That's all. I mean, there are all ways of representing a certain quantities or state of something or the values of something. So, okay. Multiplication and division by a scalar. So if you are given a matrix and a scalar, you can multiply like this. At that time you have to multiply each and every element of it. Okay, 2 into 1, 2. Similarly 2 into 4 by 4. 2 into 4, 8. And you can also divide like the way you have multiplied. And you can simplify sometimes matrix by taking out something common. So here 1 by 2 can be taken out to make this matrix look simpler. Matrix addition and subtraction also possible. So the only condition is the number of elements, the number of columns and the rows should be equal when you want to add. So they should have same number of rows and columns. And addition is done by adding the corresponding elements. Like 1 plus 5 is 6, 2 plus 6 is 8, like that you have to do. So once you do my addition, you can also do subtraction. Matrix multiplication is little different, but you will understand once you know the process. Suppose you are given two matrices of n by m size, which means n rows and m columns. So n rows and m columns, right? And you have another matrix with m rows and p columns. There are some rules for matrix multiplication. These two should be same, then only you can multiply, otherwise you cannot multiply. The number of columns of the first matrix should be equal to the number of rows of the second matrix. So if you have a square matrix, then it becomes easy, right? And the answer, the product, you can define what should be the number of rows and columns. So the result will have n by p matrix. That means n rows and p columns. Got it? So that's all. That is very simple. It looks little complex, but it is simple. Let's see how to get a couple of elements. So let's take the first row, first column element. For that you have to take first row and first column and then multiply the individual elements. A11, B11 plus A12, B21, like this. Plus you go up to the last element A1m into BM1. Good. Similarly, the first row, last column, what you do? You take the first row and the last column. You can see A11, B1p. Right? And then similarly, you go up to A1m, BMP. And the last element, what you do? You take the last row and the last column. So AN1, B1p. Good. And you go up to ANM, BMP. Great. Very simple. And we will be using these matrix operations when you are coding. Tensor product, it's slightly different, slightly, it's to a large extent different from a normal matrix multiplication. So whenever two matrices are to be tensor productized, So you express the, with this symbol, cross within a circle. And then how do you do it? Let's see how we are doing it here. So you express 3 by 4 and then 5 by 6 you do twice, because you have two elements here, and then you multiply like this: 3 into 5 15, 3 into 6 16, similarly 4 into 5, 4 into 6. So now you have got the answer. The resultant matrix is from 2 by 1 into 2 by 1 gives 4 by 1. Now you will multiply with one more 2 by 1 matrix. So at that time you have to represent like this. You get same thing. And now the resultant matrix is 8 by 1. So you have to remember that. So that's what happens when you are working with 3 qubits. Such things will happen. And you can also represent like this 0 state of 1 qubit tensor product of another qubit with the same state. You express it like this, and then you can also express it like this. So these are all ways of representing the tensor products. So you just remember, because they are all by definition. People, scientists, mathematicians, they have been following it, so we will follow it. Only you have to remember. Okay. And then inner product is slightly different to tensor product. First of all, the expression is slightly different, right? Here you are given two vectors, and their inner product is given like this. And how do you get that? First you have to take the complex conjugate of this vector and then multiply with this, like each element, and then add that, and the result will be always a scalar. This is an interesting thing. So let's take an example to make things clear. So v is given by 1 0 like this, v2 is 2 3, and then complex conjugate you have to here, since all are real numbers, only the transpose will take place. So this 1 0 will become from column vector to a row vector, and then this will remain same. You multiply this time you will do a normal matrix multiplication. So 1 into 2 plus 0 into 3, the answer is 2. Got it? Okay, so unitary matrix. So this is very, very important one. It's because all the operations, whatever gates we have, they're all nothing but applying a unit, multiplying a unitary matrix on the given state. So what is that unitary matrix? It's a complex square matrix in which its conjugate transpose is also its inverse. So let's understand what is square matrix. Square matrix is nothing but matrix in which the number of columns and rows are equal. Looks like a square. So it can be 2 by 2, 3 by 3, n by n, anything. Some of the examples are given here, and the elements can be anything. This is applicable for any matrix, right? Then a complex conjugate is nothing but, we have seen earlier when we saw a complex number, the imaginary portion should be negated. So 1 plus 2i become 1 minus 2i, I plus i is becoming minus i. These two numbers won't get changed. So that is expressed like this, and some people express it in a different way, but you remember that, whichever textbook you are following, you just remember that. Now we have to do the transpose. So typically transpose, when we say we are doing, the diagonal elements won't get changed its position, only the other elements they'll get swapped. So normally we are expected to do all, exchange the rows with the columns. So the minus 5 and minus I will get their positions interchanged. So this is the complex conjugate transpose. Got it? So unitary matrix is a complex square matrix in which its conjugate transpose is also its inverse. We are not going to see what is an inverse of matrix now, because that will go to another area of work. But we will limit ourselves to understanding of inverse matrix. You know that whenever the matrix A is given and multiply with its inverse, so what do you get? you get an identity matrix. So that's all we'll remember. Okay, so this is unitary matrix, and then I'll try to simplify by taking off out. So this is the matrix. I need to multiply with its complex conjugate transpose. So first that will also will have 1 by 2, then we have to do some operation. So this will become a negative, positive, negative, positive. So that's what is happening here. Fortunately, this is a special matrix in which the rows are and columns are same. So when I do the transpose, it doesn't make any effect, and so I can now multiply. So when I multiply, there are half into half, 1 by 4, and I'll have to multiply first row to get the first row, first column element. So I'll multiply 1 plus I into 1 minus I, and then plus 1 minus I into 1 plus I. So 1 plus I into 1 minus I is 1 square minus I square, which is 2. Oh, verify it. Plus another 2. So this will become 4. And in order to get this element, what you have to do is first row with second column. 1 plus I into 1 plus I plus 1 minus I into 1 minus I. So it becomes 1 plus I whole square plus 1 minus I square. That will be 0. How? Again, you can compute. So similarly, we got all the elements. Now I'll take 1 by 4 inside. It will become 1, 0, 0, 1. This is nothing but identity matrix of size 2. So all identity matrices will have a diagonal element as 1 and remaining element as 0. So from this equation, we are seeing that whenever I multiply matrix with its complex conjugate, I am getting I, which is nothing but A minus 1. So conjugate transpose is inverse in a special matrix called unitary matrix. So this is not the case always, please remember. In fact, for some of the matrices you don't get the inverse itself. So we'll stop at this point and move forward. Unitary matrices, all quantum logic gates are represented by unitary matrices, and they are reversible. So this is important. So we'll take one gate. Anyway, all the gates we'll be seeing it later, but let us take an important gate. So that gate will apply to this state of a qubit. Okay, it is in 0 state. So and every gate will be expressed by a unitary matrix. So that is what we are saying here. And this can be represented by a column matrix. Now I need to multiply. So it is 1 into 1 plus 1 into 0. Similarly, 1 into 1 minus 1 into 0. So you get 1, 1. And this can be expressed because now this has got both values. So this is nothing but 0 state plus 1 state by 2. That's why Hadamard gate, what it has done is from 0 state, it has moved to some special state of qubit. What is that? Entangled? No. It is superposition. That is from absolute 0 state, it has moved to both combination of 0 and 1 state. So that's why Hadamard gate is very important. And now we are going to apply Hadamard again and see what happens. So we are going to apply on this result. So Hadamard gate is now, we are bringing from there, and this can be represented, we have seen as 1, 1 in column matrix. And then again you do matrix multiplication, 1 into 1 plus 1 into 1. Similarly 1 into 1 minus 1 into 1. So you get 2, you get 0. Then you take off inside, because you have 1 by square root, 1 by square root, you got off. You get 1 by 0, which is nothing but 0 state. So this is like a magic, right? You take any state of qubit, you apply Hadamard gate twice, you will go back to the original state. So that's why it's called reversible. And finally we will see some of the definitions, so that you may come across. That's why otherwise actually there is no big need, but and particularly this is very confusing thing. We'll leave it for some time. Then basis of a vector. So again you try to know the minimum things. So basis of a vector space is a minimal collection of vectors. We don't want to have too many vectors. The minimum number of vectors such that every vector in that space can be expressed as a linear combination of basis vectors. For example, you have, suppose I put your two-dimensional plane, and then I can represent any vector. For example, I'll say 2 and 3. I can represent this vector as a linear combination of these two vectors. So how is it done? So I can multiply this vector by 2, then this vector by 3, and then add both. I'll get 2, 3. It's not only this vector. I can represent every vector in this space as a linear combination of this. So that is, then these two vectors are called basis vectors. That's the fundamental, building block kind of thing. Not necessarily that they should be 0, 0, 1, 0 or 0, 1 like that. It can be of any other thing. In fact, this also a basis vector, but that is in the complex plane. Okay, and computational basis is a special form of basis. So what is that speciality? It's simply the basis vector states composed by the distinct quantum states that a qubit can be in physical state. It can be there in physical, like we have seen qubits can reach 0 and 1 state, right? And that can also be measured. So in our case, 0 and 1 are computational basis, but we need not limit to that. It can be anything else also, but just for your information, you don't have to break your head, because they're all only for definition's sake. If A and B are vectors, then their dot product. We have seen the dot product earlier, right? So when theta is pi by 2 radians or 90 degrees, you get 0. So which means what? When you will get 0? When you have two vectors A, B, and when this is 90 degrees, you get dot product 0. And then they are called perpendicular vectors or orthogonal vectors. Why orthogonal? Just to confuse us, but we don't. Now we know, we will not get confused. And when orthogonal vectors have unit length or the magnitude for their unit length, then they are called orthonormal vectors. Basically, they are all normalized to 1. What happens? Suppose I have 3 dimensions. How do I know whether given vectors are orthogonal or not? What you have to do is you take 2 each pair. Suppose you have, then if it is a 3-dimensional, you have 3 pairs, right? So each one should have this characteristics. Then all the 3 are together orthogonal vectors. So we have just finished the minimum essential mathematics. I'm sure they are not sufficient to become an expert, but I think they are sufficient for us to get into programming of quantum computers. So see you soon in the next part.